So thank you everyone for joining for our 15th Sussex Data Science Meetup. As you can see, the Sussex Data Science Meetup is sponsored by a few different organisations. So we have support from the Data Intensive Science Centre at the University of Sussex, Silicon Brighton and Mojique. So Mojique's a search engine with a no tracking policy. So if you're looking for an alternative to Google, I'd highly recommend them. Okay, so then moving on for a bit more details, we've got Silicon Brighton, which is a community initiative, and we've got Steve Rackley here, who'll just give a bit more of an overview. So handing over to you, Steve.
Thank you, Pete. Following from what Pete said, I want to say a massive thanks to everyone for joining us today. So I think I know most of you already, but my name's Steve. I'm one of the founders at Silicon Brighton. As always, super chuffed to support Sussex Data Science. Still great memories. The first meetup I attended, going back a few years now. So yeah, super chuffed to be here. Just so, in case any of you don't know about Silicon Brighton, we're a community-led initiative to support digital growth in the city. We began back in late 2019 by working with local groups to help raise their profile and provide everyone with free opportunities for networking, training, upskilling and development. We've supported about 80 odd events now, and we've given a platform to hundreds of speakers to share their knowledge. If you haven't come across us before, then I'd urge you to take a few minutes later to look at the website. It's siliconbrighton.com. You can learn there about upcoming events and browse through some of the great resources and speaker talks from previous sessions. And you can also sign up to our newsletter via the website footer, which will help you stay informed about everything that's happening locally in tech. And that's it from me. I hope everyone enjoys today's session. And yeah, thanks for coming along, and Mel too. Really appreciate your time.
Thanks.
Cheers, Steve. And we've got a QR code there. So if you want to get your phones out and scan that, that'll take you to the Silicon Hub, where you've got a lot of the information Steve just talked about. Okay, and then moving on. So the Data Intensive Science Centre, which I work at, we're a kind of research unit at Sussex University, which focuses on data science. So we help with providing training and collaborations across different disciplines within the university. But we also offer some of the expertise we have to the wider community and businesses. And that can take form or numerous forms. That can be through things like hack days, where if, for example, you've got a particular problem that you'd like to explore, we can get together a hack day where we'll have numerous students come and look at your problem and explore it. And of course, a very intensive day. So you can go away and, having had the problem explored, and decide where to go next with it. We can act as research partners for grants, such as the Innovate UK grants that come out. We can also provide traditional consultancy. And one of the other kind of main things we can offer is student placements, and that can be either MSc data science students or PhD students, and they can act. That can be very useful if you need an extra pair of hands to explore that particular problem, which maybe you just haven't had the time or resources to explore. Okay, so that's most of the information about Silicon Brighton Discus. So moving on to the main event. So Dr Melanie Ades has very kindly agreed to talk today. So just to give a bit of a background on Melanie, so she did an undergraduate at Sussex University in mathematics with computer science. She then went on to do a PhD at Reading in mathematics with meteorology, followed by a postdoc, and then moving on to doing catastrophe risk modelling, risk management solutions, and then moving on to her current position at the European Centre for medium range weather forecasts. So handing over to you, Melanie.
Thanks, Pete. Okay, I would like to start the presentation by just talking briefly about what the Copernicus programme is and how the Copernicus Atmosphere Monitoring System fits into the Copernicus programme. So the Copernicus programme is part of the European Union's efforts to manage or reduce their carbon emissions. Its tagline is Europe's Eyes on Earth, And its aim is to harness world-leading science and technology to equip society to understand and adapt to our changing environment. And this world-leading science and technology and the eyes on Earth are the Sentinel satellites. This is a constellation of satellites, the first of which was launched in 2014, with another dozen, I think, to follow over the next 10 years. These satellites fall into 6 different groups of satellites, 3 of which consider atmospheric composition or air quality observations. But the Copernicus program isn't just about these Sentinel satellites, it's also about using the information from these satellites to equip society to understand and adapt to our changing environment. So what this means is that the European Commission have introduced 6 services, and these services take the information from the satellite observations, but also from in situ, so ground-based, basically, infrastructure. And they turn these observations into information that's more easy to use or directly applicable to people such as policymakers, the public, and the private and commercial sector. Of these 6 services, 2 of them are actually run by the European Centre for Medium Range Weather Forecast, and they're the ones in the dashed lines there. So the Climate Service and the Atmosphere Service are both managed by ECMWF. And I work for the Atmosphere Service. So this takes the atmospheric composition observations and turns it into information on air quality that can be used by policymakers and the public. So what is the Copernicus Atmosphere Monitoring Service, or CAMS? Well, it's formed of 2 different parts. One part is a global model that uses satellite information to understand the air quality globally. This forms the boundary conditions for a series of 7, I think soon to be 9, regional models that use both satellite observations but also in situ observations and cover just the European domain. The information from both the global model and the regional models is free to anybody and is used by people such as national agencies or small, medium-sized enterprise, citizens and scientists. And it's the global model specifically that is run by the European Centre for Medium Range Weather Forecasts and is part of and based on their numerical weather prediction model called the Integrated Forecasting System. And this is where I work. So what do we actually produce? Well, we produce 2 5-day forecasts of air quality. These are initialized at midnight and midday every day. These forecasts run on a gridded domain, which has a 40-kilometer horizontal resolution and runs at 137 model levels up into the atmosphere. And we have lots of different products that we produce, but perhaps the main products are aerosols. So this is related to anything that is small particles in the atmosphere. So you're looking at smoke, dust, sea salt, but also perhaps the output from volcanoes, anything that's likely to produce small particles in the atmosphere. And we also run forecasts of reactive gases, which would be carbon monoxide, formaldehyde, nitrogen dioxide, ozone, sulfur dioxide, and many more different species. And you can find all of this information on our website, and it's freely available and downloaded by anybody who's interested. So I show here an example of one of our 5-day forecasts. This uses CAMS data of sulfur dioxide, but it's run through the Windy app. And it's from this last weekend. So this forecast was initialized on Saturday, the 10th of April, and it shows the eruption of the La Soufrière volcano that happened at the weekend. And what you can see here is how the sulfur dioxide that was released by that volcano is being transported across the North Atlantic towards Africa and potentially maybe towards Europe in the end. And so this helps us to understand, or policymakers to understand, if there's likely to be an impact to the air quality over Europe from the eruption of this volcano. Now, where I specifically work is that in order to produce this forecast, we first need to understand what the initial conditions are. So we need to understand what the sulfur dioxide is at the time we make that forecast in order to be able to accurately forecast it into the future. And because we work on this gridded domain, what we really need is the initial conditions on the model grid. So here I show a grid box representation of the atmosphere. So we have all the grid box and grid points horizontally around the globe. And also we have all these points that go up into the 137 model levels of the atmosphere. And we need this initial condition and all these points in order to be able to run our mathematical model that then propagates this information forward in time to produce our forecasts. Now, we do have observations coming from these satellites of what the sulfur dioxide is. So this is an example on the Sunday, so on the 11th. And it shows the sulfur dioxide observations from the Tropomi instrument, which is on the Sentinel-5P satellite. Now, in the past, people have said to me, well, why can't you just use the observations and take those, that's as close to the truth as we're going to get, and take those observations and use those as the initial conditions. But unfortunately, if only it was that straightforward. So I show here a whole series of the observations that we have from the different satellites over a 12-hour window. So you can see that there's 1, 2, 3, 4, 5 satellites that give us ozone information. And you can see them in each of the different colours there on the top left-hand plot. Similarly, for carbon monoxide, we have the 2 different observations, NO2 and SO2. And the first thing that stands out is that there's these large gaps in the observations over this 12-hour window. And for most atmospheric composition or air quality species, we take the measurements in the UV or visible spectrum, which means that when we need the sun to make the observations, so when we're in a nighttime situation, we have no observations given to us from the satellites. It also means that where you have cloud, you don't get any observations. You need that direct path from the sun down to the Earth and back up to the satellite. Furthermore, we often or mainly use lower Earth orbit satellites, which means that they have a fixed overpass across the globe, and it can take, therefore, a few days before we get global coverage. You can see here the swath lines of the satellite as they move across the globe, and there's large gaps between those swath lines. And as the globe rotates, we will cover those large gaps, but it will take a few days before we have information across the complete globe, taking into account the nighttime and the daytime issue as well. One final problem is that we, mainly for atmospheric composition, get total column observations, which gives us pretty much no information on the vertical distribution. So although we might understand what the total column of nitrogen dioxide does, we won't know where in the atmosphere that nitrogen dioxide lies. So all of these things mean that we can't really use the observations directly to give us our initial conditions to then forecast forward in time. And we have to make some sort of, use these observations in a cleverer way to understand what the initial conditions are. So what we actually do is we consider the initial conditions to be a probability density. So what we're looking at and what we want to understand is actually the probability of our grid box model state at our initial time, given that we have these observations Y. And we can use Bayes' theorem to transform this. So Bayes' theorem tells us that this probability density function is proportional to the probability of our observations given our gridded model state at our initial time times the probability directly of our initial gridded model state. But what does this actually mean, and what is our gridded model state? Well, we run by sitting on top of a numerical weather prediction model. And for our numerical weather prediction model, there are 5 variables. We have vorticity, divergence, temperature, surface pressure, and specific humidity. Then on top of that, for atmospheric composition, the species we're interested in for our initial conditions are ozone, carbon monoxide, nitrogen dioxide, formaldehyde, sulfur dioxide, and aerosol mixing ratio. Now, looking at each one of these variables on the grid, we operate on a 40-kilometer horizontal resolution, which leads to approximately 350,000 points around the globe. And that's just for one horizontal resolution. So then we look at those points going up into the atmosphere over 137 model levels, and we end up with around 50 million points for one variable. If we look at that across all our variables of our model, we're looking at a space of about 500 million points. So we're looking at a probability density function over a very high dimensional system. It's also quite nonlinear. If you think back to the forecast of the sulfur dioxide, you can see all the eddies and flows of the sulfur dioxide as it follows the winds around the globe. And so what we're looking at is not a straightforward probability density function, but it's actually something very complicated with many different modes. In addition to this, we also have the observations. So here are just the observations that we use in our system for atmospheric composition species. We also have all the observations of the numerical weather prediction variables. And of these observations, I've taken one as an example, which is the Sentinel-5P satellite. It's the ozone observations that come from the TRPOMI instrument on the satellite. And for this, we get about 250,000 observations in 12 hours. Now, this is quite a fine resolution instrument. It's quite new. So that is quite a high number. But still, you can see we have many thousands of observations that we're also using. So we're looking at a very high dimensional system. So how do we deal with the fact that we need to understand our initial condition from this probability density function for such a high dimensional system? What we have to do is we have to make different assumptions, and different weather prediction centres make different assumptions, and that can affect how you establish what your initial condition is. And at the European Centre where I work, what we do is we work over a 12-hour time window. So we're interested in all the observations over a 12-hour time window. And what we want to establish is our initial condition at the start of this 12-hour time window. And what we do is we make the assumption that this initial condition is a Gaussian distribution. This is a gross simplification of what is actually a very complicated probability density function, but we have to do something to make the problem tractable in such a high dimensional system. And so this is what we do. We assume that the mean of this distribution, the XB, is a short-term forecast. So it's a 3-hour forecast from a previous time that we propagate forward in time for 3 hours, and we say this is the mean of our distribution. And then what we're looking for is the probability of X0 as it varies, here shown as an example in just the one dimension. So we take this short-term forecast, this 3-hour forecast, and we say, right, that's our first guess at what we think our initial condition is. And then we propagate it forward in time for the 12 hours. And that's the dark blue line you can see. And we understand that there's some uncertainty in that forecast forward in time. And that's our error covariance that we represent by, at the initial time, by this matrix B. That's our error covariance of our initial forecast. So having propagated this forecast forward in time over the 12 hours, we then look at our observations, which are shown here with the dark blue dot with the surrounding lighter blue uncertainty. And we say, well, we're going to assume that this is a Gaussian distribution. And sometimes this is not too bad an assumption, but it can also be not a great assumption. So we represent it as a Gaussian. And what we're interested in is what the probability of this observation is given this model state. So we're basically comparing the model state propagated forward in time to the correct time of that observation to the observation. And here the H of X is because we have the model state, which is a gridded representation of our atmosphere, and we're comparing it to our observation. And as I've already mentioned, our observations of atmospheric composition are often total column observations, for example. And we have to take our gridded model state and turn that into something that's equivalent to the observation. So that's what H does. It takes the model state and it interpolates it to the location of the observation, and it turns it into an equivalent representation of the observation. And R, again, is our error covariance, but now it's our error covariance of our observation. And what we do is we combine these two and we try and use it to understand what the probability density of our initial condition actually is. And we do that by balancing how far we move from our background model state, our initial forecast, with how much that leads to an improvement in our forecast across the 12 windows that brings us closer to the observation. So the green line, you can see, is very close to our background in the schematic, is very close to our background model state in the blue line, but it's shifted slightly, and that enables us to match our observations much better. We're now following the path of our observations. So as a simplification, that is what we're doing with our data assimilation process. So combining these two different probability density functions leads us to a cost function. And what we're trying to do at the European Centre is find the minimum value of this cost function, which is the most probable, the maximum likelihood state of our initial condition. So again, we're working over a huge system. So if you think our background state is 500 million, then our error covariance matrix, well, that turns into about 3 to 10 to the power of 17 information. And even with our R is also very high dimensional. And so we solve it using a gradient descent method, but because it's such a huge system, we need to make even more assumptions than just the Gaussian assumptions that we've already made. And the main assumptions we make relate to these covariance matrices, B and R, that we just simply can't store on our computers. Even though we work on these huge supercomputers, we just don't have the space for storing matrices of that size. And so we make the assumption with B that species are not cross-correlated. So your wind speed has no effect on your temperature gradient in the atmosphere. So each species is totally separated. And with R, we go even further and say there's no correlation within a species. So R becomes purely a diagonal matrix, and we can just store it as the same size as our observational vector Y. So this leads to some quite interesting mathematics, and for the mathematicians amongst you, I just wanted to briefly run through what I think are some of the more interesting mathematics of this equation. First of all, with B, I've already said we have no cross correlations in the matrix, but that still leads to a matrix that's far too large to store on our supercomputers. So what we do at the European Centre is we represent B in wavelet space. This means that instead of representing B at every point around the globe, we just store it at certain points that we need to represent our wavelets of different sizes. This enables us to reduce it a lot more, and there's quite a lot of interesting maths around how we do that and how we transform the whole problem into being a problem in wavelet space. We also have our representation of observations from satellites. So we get a huge amount of information from the satellites, and it's whether we can make transformations to those observations to reduce the amount of storage of the observations. So I'm not talking here about data reduction. I'm talking here rather than reducing the bit storage of the actual observations, I'm talking about, can we apply transformations to those satellite observations that retain the information but also reduce the size of the observations. So there's quite a lot of interesting mathematics around the transformation matrices needed and precursors and things like that, and information that's correlated across different observations that goes into looking at reducing the representation from of observations from satellites. We can also reformulate the cost function. So I show here the cost function in grid point space, but it's also possible to represent the same cost function in observation space. And there's saddle point algorithms then for solving that cost function in observation space. That means we can solve the function in parallel, which obviously speeds up hugely the speed at which we solve the function, because not only in an operational system do we have restraints on the size of the data we can store, but we also have restraints on the speed at which we need to solve the cost function. I think we have about an hour to establish this initial condition before the forecast is required, because we get a very short time window in which to produce and give this forecast to our European member states. Finally, I've showed here one particular solution of the probability density function, but different weather forecasting centres use different methods for solving that probability density function and finding the initial condition. And so, for example, the Canadian Meteorological Service use an ensemble Kalman filter, which has basically is an ensemble representation rather than a single cost function. But this has its own issues to do with trying to represent such a huge system with an ensemble of model states. And there's quite a lot of interesting mathematics around what you do to try and make that work. So, leaving behind the mathematics, I thought I would show a couple of examples of this data assimilation in practice. So this is an example from February of this year, we had a couple of dust storms in February of this year that took desert dust from Sahara up over the Mediterranean and even as far as the UK. So you can see here, the top left picture is a picture of an amazing sunset, and that amazing sunset is created probably because of all the dust in the atmosphere. More of an impact is the center picture. This is actually the snow in the Alps, and that's the desert dust deposition on top of that snow, which makes it almost look like a desert. That's how much dust then outfell over the Mediterranean. And you can really see that clearly from this time shot in the top right-hand corner. This shows the progress from the morning to the afternoon of when that dust storm came across. So you can see the top picture quite clear. You can see all the white snow. And then as the desert dust came across, you can really see what a huge impact this has. So this was our forecast, our initial short-term forecast for one of these dust events. This is on the 22nd of February. I don't know if you can see it very clearly, but you in the center of the picture is Africa, and there's your desert dust, and actually quite a lot of it is going across the North Atlantic towards the Caribbean. But there's this one big plume that's coming up across the Mediterranean Ocean, and then across France and actually up to the UK. So this was our first guess of what our initial conditions would be to make this forecast that would go forward in time. And then alongside that, we have our observations. So this comes from the instrument called the MODIS instrument on board 2 American satellites, the Terra and Aqua satellites. And these are the observations we get in a 12-hour window. So our short-term forecast was valid at 3 a.m. on the 22nd of February. And we're interested then in observations from 3 a.m. to 3 p.m. across this 12-hour window. And you can see the gaps in the observations. Part of that is from the swath of the satellite, and part of that is because there's cloudy conditions. And some of it is even because you have really heavy desert dust. The algorithm that produces the satellite observations can't necessarily tell whether it's cloud or desert dust. And so it will assume a worst case. It will assume, unless it thinks otherwise, that you're actually got a cloudy situation rather than desert dust. It would rather give you no observation than give you a wrong observation. But you do still have some information here, and this can help inform us on how well we've done with our initial forecast. And what we often find with our initial forecasts is that perhaps the plume is in slightly the wrong place. And so the observations can help to shift that plume or to adjust the magnitude of that plume to lead us to have better forecasts going forward in time. So here on the bottom row, you can see the initial conditions following the assimilation of the observations. So on the left, it's valid at the same time, but now we've taken into account those observations across that 12-hour window. And on the right, you can see the difference between the initial forecast and then those initial conditions that we end up with. And you can see there's quite a lot of adjustment of the model state goes on. You can see this by, obviously, the red is where we've increased the aerosol, and the blue is where we've decreased the aerosol. And what I show next are those observations superimposed on top of that difference between the initial condition and the short-term forecast. And there's a couple of interesting things that we can see from this superposition of the observations on top of this increment. The first is that you'd expect the increment to line up with the observations. So you'd think that where you had an observation, you'd see an adjustment. And what you can see here is there's actually quite large adjustments where we have no observations. But what you have to remember is that the observations occur over a 12-hour window, and our increment, our change to our initial condition, is just at the start of this window. So what you might be seeing is an observation here of aerosol optical depth, but actually this increment is the initial condition that you need that is then moving up to where that observation is at observation time. What you also have is that you have your B matrix. So you can see that you have an increment, a change to the system across most of the domain that I'm showing here. And obviously we don't have observations everywhere, even taking into account our 12-hour window. But our B matrix in each individual species will propagate our information from where the observation location is to other areas. And so it's quite important, our B matrix, because it really helps us to qualify where the information that comes from observations is actually used throughout the system. And I have a second example here that really highlights this. So this is an earlier volcanic eruption, not the one from this past weekend, but this is one from June and July of 2019. It's the Reikoko eruption, which occurred on a small island off the coast of Japan in the North Pacific. And on the left, I'm showing again the Sentinel-5P observations. These are the near real-time total column observations, again, of sulfur dioxide. And on the right, I show what these observations actually mean in terms of producing initial conditions in our system. So this is, I call this as our standard assimilation run. So the process of incorporating these observations into our system is called data assimilation. And so this standard assimilation is what our system would produce in terms of a vertical distribution of that sulfur dioxide from these observations. Now, what's quite interesting is that these are total column observations. So why is this information distributed at this specific location? And that comes from our B matrix. Now, our B matrix we generally create using statistics from our forecasting model. But the statistics for sulfur dioxide related to volcanoes are not really appropriate. We have very few volcanoes that are released, so trying to gather the statistics from them is tricky. They're also throughout the globe, they're at very many different heights, very many different types of eruptions. So it's very hard to form appropriate statistics to use in our B matrix. So what we actually do is we look at the volcanoes, we look at the height of the volcanoes, we take a sort of average height of a volcano and say, well, actually, we think that most of the information from the observations is applicable to a height of 500 hectopascals. So we're assuming this is an approximate height of where the volcano erupts and that sulfur is ejected into the atmosphere. And so we sort of artificially superimpose a background error standard deviation onto our B matrix that controls where the information from that total column observation is input into our system. So new experiments that are just recently being run actually use a new product that comes from the Sentinel-5P satellite that includes a layer height. So not only does it have a total column observation, but it also says, well, although this is a total column observation, we think that most of that sulfur dioxide lies between a pressure at the top and a pressure at the bottom of this column. And so we now can incorporate that information when we're using this information and this observation, and that allows us to much more accurately look at where that sulfur dioxide will actually be released vertically in our forecasting system or in our initial condition. So you can see here that for the same information, the same assimilation, we now have sulfur dioxide much higher in the atmosphere. And this could have quite a large impact because you can have winds that vary quite strongly as they go up through the atmosphere. So if you release sulfur dioxide too low, it may tell you that your sulfur dioxide is going in one direction, whereas actually if you get the right height, it may go in a slightly different direction. Perhaps not quite so important for sulfur dioxide, but if you think of like the Iceland volcano where there was a lot of ash and the aircraft couldn't fly through it, if you get the wrong forecast for your plume direction, then that can have a large impact on where aircraft can fly. And the more accurate it can be, the more likely that aircraft can carry on flying, having confidence in the forecast that you're putting out. And we can see how that's an improvement. If we look here at the vertical distribution, so this is on two different dates, on the 26th of June and the 29th of June. You can see results from the Calliope satellite. Now, the Calliope satellite has a very narrow swath width, and you can actually see the path the satellite has followed in the two insets on both sides. And you can see here that it's a very narrow kind of overpass. So we don't get very much information from the Calliope satellite, and we actually don't use that in our system, but it provides very good information for verification. And so here I have the results that are actual observations that show the height distribution of information. And what you can see on the second row is this is with our layer height. You can see where we're placing that information on that eruption from the volcano, and then that compares very nicely with the very small information we get from the Calliope satellite. But if you look at our standard assimilation, when we have no idea of where that SO2 is released, you can see it gets released far too low in the atmosphere. So this just shows how sensitive the system is to both the observations we get, but also our background modelling, our understanding of our short-term forecasts and how we use that when we try to understand our initial conditions, and how important it is really to make sure that we get those initial conditions correct. So what I've shown you here, I hope, is a brief insight into the work I do to try and understand initial conditions for forecasting. It's very similar principle between numerical weather prediction, but how I particularly use it is for atmospheric composition modelling, and how important the satellite information that comes from this Copernicus programme is in the air quality forecast that we produce and that we disseminate to people. And I hope I've given you a bit of an insight to some of the interesting mathematics that goes on behind what initially might appear quite a straightforward problem, and the size of the dimension of the system that we're operating in, and how high dimensional it is and how we try and cope with that operationally. Thank you very much.
Brilliant. Thank you very much, Melanie. Meanwhile, I have a quick question, Melanie, if I could put that to you. So I guess, I mean, how problematic is this 40-kilometre resolution? Is it particularly problematic for certain gases? Because I can imagine for, say, like a city like Brighton, 40-kilometre grid, you're going to have both the city, local countryside and the sea. Yeah,
absolutely. It's a balance, really. So for the numerical weather prediction model, two separate models that run at ECMWF. You have just numerical weather prediction, and then you have our atmospheric composition system. They use exactly the same mathematical and computational model, but the numerical weather prediction is run at a much higher resolution because they only have the 5 variables that they need to model. We have the extra 6. And so the higher resolution we go, the better our forecasts can be. Basically, as you say, we can start to pick up cities, whereas at the moment you have a situation where you're covering both the city and the surrounding countryside. You can have a situation where your observations are much smaller scale than your grid box. And also the other way around, you can have observations that are larger than your grid box. And so it's trying to combine your operational speed with the resolution. And every time you have a new supercomputer, you might have a faster speed. You might be able to think about going up to a high resolution. As the mathematics improves and things like the subtle point algorithm, if you're able to run in parallel, then you would be able to run much quicker with much more information. And again, you'd be able to increase your resolution. But I guess we just work with our resolution as it is because that's all we can afford to run, rather than that being optimum or in some way chosen to suit the application, the atmospheric composition application.
Okay, so I guess related to that, we've got a question from Mark Harrison, and that's, would the maths lend itself to different density grids in different parts of the world, e.g. a lower density over vast tracts of the oceans?
So that's really interesting. And in fact, even more than that, moving meshes is something that people are looking into, so that you, for example, if you have a hurricane that you want to model in more detail, it's important to understand exactly what's going on with that hurricane. You might want to use an increased grid over that, and then a lower resolution grid on the rest of the world. But it's an area of research rather than an area of operations. So it hasn't yet reached a point where we can use any of that research in operations. So unfortunately, we're stuck to a fixed grid at the moment. But it's possible, but tricky to use something where it's different sizes of grids.
Yeah, I can attest to that because I used to work on these methods a long time ago. So they introduces all sorts of problems.
Yes. And it's really interesting, and some of the research is really interesting, but it hasn't progressed to a point where you can actually make the thing run on it, especially on the very large dimensions that we're actually talking about for the numerical weather prediction.
Maybe ask one question here then, just following up on the trend here. Where do you see, though, improvements and next evolution in these methods? So do you think, I mean, we mentioned computational or sort of algorithmic development and it being able to parallelize, and we mentioned just computing speeds and resolutions and flexible resolutions. What about a higher density of satellites? What about sort of observing its grid cell from multiple angles to break the column up, and etc.?
Oh, there's so many different ways. You're very right. A vertical distribution in our system, a vertical distribution of an observation that could give us vertical distribution would be one of the biggest ways that we could make easy improvements, because it's set up for vertical observations. We have vertical observations of ozone, for example, so it wouldn't be very hard to include that in our system, but the observations aren't available at the moment. So that would be an easy way to make improvements. Another way so you have a balance between, I guess for me, stuff that could make a big improvement, like the saddle point algorithm, if being able to parallelize it, but that is so far in the research, there's so much more research that needs to go into it before it could be used operationally, that we're talking years down the line. Where we can make more improvements more immediately is in things like the background error covariance modeling. In numerical weather prediction, they use very clever ensemble methods to try and get flow dependency, because we at the moment use a static background error covariance matrix. We say it's the same no matter the season, no matter the time. But you can imagine that you have very different, say, errors if you've got an ozone hole compared to if you don't have that ozone hole. But at the moment, we have some sort of average across both that we use. You also have flow dependency. So again, if you look at a hurricane, you might have many more errors to do with your hurricane, or more uncertainty in perhaps the path of that hurricane and things like that, than you do over a relatively stable weather situation. So that's a sort of computational issue. The science and the research is there. It's just about whether we can actually apply that under the operational constraints that we have in such a large dimensional system. So if there was possibilities to include some of that, somehow to speed things up to include that, I think that could be a very immediate gain in the performance and behavior of our system.
Brilliant.
Oh, great. Thank you very much for that.
Colin, I think you had a question you wanted to ask as well.
Yeah, well, firstly, thanks, Mel. A fascinating talk. Really interesting. Yeah, I don't know, expect you to have an answer to this, and it might be a case of you should talk to or look at this or use a search engine to find out, but maybe other people might have an answer. But we're a general search engine. I've been approached by companies offering, I have to be careful what I say, basically offering to their weather data services, would we display it on our search engine? And we've got one of our concerns is about being biased to particular commercial operators. So I guess my question is, we use, like most search engines, a knowledge box used from Wikipedia, right? Which is, you could say, is biased, but everybody does it, right? But so where's the Wikipedia for weather data, I suppose, with the question, or who should I talk to?
Oh, that's very. So you mean how? So something that would tell you the quality of the different people that.
Well, I guess it will be some. What's the kind of a free to use good API for weather data? Should we partner with somebody, for instance? And I don't know.
So I'm biased with atmospheric composition data.
Yeah. Well, that's interesting, because one of the people who came to us, they were actually offering quality data which is some aren't, and I guess it's coming from Copernicus. They're probably taking that data, I'm guessing. It's freely available, so we do take it. I guess we just what we give is a gridded data set. So at every time you have a grid that tells you the different quantities, which doesn't necessarily visualize very well. So something like Windy take our data but produce something that's very nice as a visual. I don't know if there's a sort of Wikipedia for all of that. I don't even know quite at the moment, because
is managed by a different team who actually even takes our data and uses that, and whether there's any of them that use it. I mean, I have the Windy app on my phone. I don't even know if I got that for free.
Yeah.
We have I tell you, the people you could ask about that is we have a user support system. If you look on the Copernicus Atmosphere Monitoring Service and go through help and support, we have a team of people that can direct your question to the right people. So it might be worth approaching them, saying, you're interested in your data, who uses it? Whether there's anyone that then passes it on in a better form.
I mean, I guess it'd be a case of saying, if I can get a list of who uses that data, then I can troll through that.
That they should be able to give you. I don't see why not. It can't be. I don't assume it's not commercially confidential, and all the people that use it would want to be known that they produce these forecasts. So I'd definitely start there as a place.
So that's the Copernicus help.
Yeah, if you go to the Copernicus Atmosphere Monitoring Service, then there's a link. The website pops up straight away, and there's a link to the help and support. And in the end, you'll be able to ask a person directly.
Thanks very much. Okay.
Brilliant. I guess we wrap up the questions there. So just to finish off, so we've got the Brighton Data Forum, which is a kind of sister meetup to the Sussex Data Science meetup. We've got Oscar here, who does a brilliant job of running that meetup. So their next meeting is on the 26th of May at 4 p.m. And they also have a Slack channel where a lot of the kind of Brighton community ask questions and send information on about data science and data science opportunities within Brighton. So highly recommend joining that. So the QR code there will take you to the sign up for the Slack channel. Oscar, if there was anything you wanted to add about that quickly.
Thank you. Yeah, sorry. This is tentative yet, but I'll give you the scoop that next time we might be discussing data governance. So I should start at the beginning. The Brighton Data Forum is a broad church forum for data professionals. It is not specifically focused on data science, although lots of data science happens there as well. So we take into consideration data engineering, data ethics, data in society, and wider topics. And all things going to plan, and we have tentative plans now to discuss data governance in the next couple of meetings. We've got some really good speakers lined up, and I'll wait for confirmation before announcing who they are.
Brilliant. Thanks, Oscar. And that just leaves me to wrap up. So we've got our next meetup on the 17th of June at 4 p.m. And as always, if you'd like to talk or you know someone who would be a good speaker, then just get in touch. The QR code there is to sign up for the meetup for the next meeting. Otherwise, thanks again, Melanie, for your talk. Look out for it on our new YouTube channel, and take care and see you next time. Thank you very much.
Thank you.